Hi Calc students, welcome to our section on 2.3 Part 1 where we are going to learn two new very important rules for derivative, which is product and quotient rules. We are also going to practice taking some higher order derivatives using product and quotient rules. Okay, so what is the product rule? Well, you know what? Before I tell you what it is, let me tell you what it is not, okay? When you are taking the derivative of the product of two functions, so f times g, it is not equal to f prime times g prime. Okay, guys? So don't do that. Don't just take the derivative of each function and multiply it together, because that is what it is not. Here's what you're going to have to do. You're going to have to take the derivative of the first times the second plus the derivative of the second times the first. That is what the derivative of a product of two functions turns out to be, okay? Now, I know some textbooks write the rule this way, so I would like to show you all the different ways in which you might see this rule, because some of you might have tutors or maybe look up other stuff online sometimes, and even might have some AP Calc study materials. And so sometimes you'll see the same rule written like this. And so it would be u prime v plus v prime u, where u is just representing one function of x, and v would be representing a different function of x, so f and g. And then u prime would just be the derivative of the first function, and v prime would just be the derivative of the second function. So some textbooks like ours just goes ahead and uses function notation. Other textbooks like to use what's called like a u and a v substitution. It's really helpful to see it both ways. Okay, now that's for product rule. Okay, but then for the quotient rule, it's a little bit more involved than just that. But look at the numerator here. It's very similar to the product rule because it's f prime times g and then g prime times f, but it's subtracting the two instead of adding them. And so it's very important that you use the correct order. So the order matters in this numerator because of that subtraction. So it's always the derivative of the top one first. Derivative of the top times the bottom minus the derivative of the bottom times the top. All of that is being divided by the bottom squared. So again, the other version of that using u and v would be u prime v minus v prime u all over v squared. Again, u is just one function of x. V is a different function of x, and then u prime and v prime are just their derivatives. So it's just important to remember that the product and quotient rules don't work the same way as the sum and difference rules. So again, what the product or what the quotient rule is not is if you are dividing two functions and then taking their derivative, that is not equal to just taking each derivative separately and dividing. It just doesn't work out to be that way when we use the limit process. And so after learning that lesson, we now have these different rules. So we just have to abide by them. So this is what we use for product rule, and this is what we use for quotient rule. So let's try it with example 1. Another really important thing too is like recognizing what a product is. So this right here is a product of two different functions. I'm going to write it a little bigger so we can kind of see. So the x is a linear function, right? X to the first power. And the e to the x is an exponential function. So these are two different functions. And so you could think of x as our f of x, and you can think of e to the x as our g of x. So maybe I'll write that off to the side here. So we really have two different functions, And so what we'll do is we'll find each of their derivatives. So f prime of x when it equals x is just 1, because remember the derivative is just the slope of the curve, and for a linear function the slope of the curve is constant. So the derivative will be constant and it will equal that slope. And the derivative of e to the x, my favorite one, is just e to the x. So these derivatives separately are very simple. But we will need to use the product rule in order to find h prime of x. So h prime of x is going to be, maybe I'll just write out the rule first, f prime g plus g prime f. F prime of x times g of x plus g prime of x times f of x. So then f prime was just 1, g was e to the x, g prime was also e to the x, and f of x was x. So then h prime of x is equal to e to the x plus x times e to the x. Or you could write that as e to the x times 1 plus x. Either way. E to the x plus x, e to the x, or e to the x times 1 plus e to the x. And that would be our full derivative of this function. Now over here in part B, it's a little more obvious that I have two functions, right? I have one that's a radical function or a root function, and then a second one that's like a polynomial, or more specifically a quadratic. So I could maybe call this first one f of s and this second one as g of s. So f of s would just be the square root of s, which I think I'm going to rewrite that as s to the 1/2 to make it a little easier to find the derivative. And then g of s is s squared plus 8. So then f prime of s would just be using the power rule. It would be 1/2 times s to the -1/2. And g prime of s would just be 2 times s to the first plus 0, because derivative of a constant is 0. And then p prime of s would be, well, it would be this. Let's write it out long first. So it would be f prime g plus g prime f, all evaluated at, or all with s's plugged in. So, because it's derivative of the first times the second plus derivative of the second times the first. So then if I plug everything in that I have, that would be 1/2 s to the -1/2 times s squared plus 8 plus 2s times s to the 1/2. I'll leave it in exponents for now, and then I'll switch it to radicals. Okay, so this is the derivative I get. And there's two ways that you can simplify this. And I think the book shows both as well. But it is important that you do know how to simplify it in both of these ways. So let me show you the common denominator method first. Okay, common denominator method would say, all right, let's put all these s's to the 1/2 power back into their square roots. So I want to point out something. This one would end up in the denominator along with the 2, because exponents to the negative power go to the denominator, and 2 is already in the denominator. So that's why I'm saying you're going to need a common denominator, because right now we have 1/2 square root s. Actually, let me just go ahead and put s squared plus 8 in the numerator. So I have s squared plus 8 over 2 times the square root of s plus 2s times the square root of s over 1. And I'm going to want to get a common denominator between these two in order to simplify this. So what I'll do on this side is I'll multiply by a 2 and a square root s, 2 and a square root s, so that they'll have a matching denominator. So then when I do that, I get s squared plus 8 here, plus, I'll do 2 times 2, so that's 4. And then I'm going to have this s times another s, because when you do the square root of s times square root of s, that ends up being s to the first. So s to the first times s to the first would be s squared. And then now it's all over a common denominator of 2 times the square root of s. But now if you notice, I do have some like terms. I have an s squared and a 4s squared. So I can combine them. So now I have this 5s squared plus 8 all over 2 times the square root of s. And that is one version of a simplified answer for p prime of s. Okay, so we would want to simplify it into this form or a different form. So this is the common denominator form. And then I'm going to show you another form. Why am I showing you another form? Because sometimes the AP test in our textbook does this, and you just have to know that that's what the heck is going on. So let me start from this line again. So let's say we just finished using the product rule, and I have this. I have 1/2 s to the negative 1/2 times s squared plus 8 plus 2s times s to the 1/2. So this is like alternative ending number 2. Okay. The other way of simplifying this is to first recognize that I can combine these s's right here by adding their powers. Because if you have a common base and you're multiplying them, you go ahead and add the powers. And then I'm going to go ahead and distribute this 1/2 s to the negative 1/2. And then I can also, when I multiply these s's, I can also add these powers. So I would end up with 1/2 s to the 3/2 power, because negative 1/2 plus 2 is 3 over 2, plus 4 times s to the negative 1/2 power, because half of 8 is 4, and then there was no s here, so you just have s to the negative 1/2, plus 2 s to the 3 over 2, because I'm adding 1 plus 1/2. Then you might notice, okay, we have some like terms. We have 2 terms with s to the 3/2 power that I can combine. So then I get 1/2 plus 2, which is 5/2, 2.5 or 5/2, s to the 3/2 power, plus 4 s to the negative 1/2 power. So we could simplify it down to here, and then what we're going to do, and this might seem really odd, and so I apologize ahead of time, but it is a thing that you need to maybe learn now and study for future, but we're going to factor out a 1/2 s to the negative 1/2. It kind of does go along with the answer we got simplifying it this way, because if you look at it, you could kind of think of this as being multiplied by 1/2 s to the negative 1/2. But whenever we have an expression like this where we have s's to positive powers and s's to negative powers, or like any variable to a positive power with another variable to a negative power, we generally factor out the negative power, and you're going to see why. And then similarly, we have a fraction and a whole number, so we're going to just factor out the denominator. So let me show you what happens. So technically, when you're factoring out, let me make some space here actually. When you are factoring out something, what you're technically doing is dividing all of the terms in your expression by whatever it was that you factored out. So if we're factoring out a 1/2 s to the negative 1/2, essentially what we're doing is dividing both pieces by that. So when you divide, and we'll do that over here, I'll do some scratch work over here. When you divide 5/2 by 1/2, what you're really doing is multiplying it by the reciprocal. So the 2's cancel, so it gets rid of that denominator. So this 5/2 turns into a 5. But here's the thing that is the real reason why we do this. If you divide something that is to a positive power by something to a negative power, we think of that as s to the 3/2 over 1 over s to the 1/2, because a negative power means take the reciprocal. But when you're dividing, you end up multiplying by the reciprocal. So I'm going to end up multiplying by s to the positive 1/2 over 1. Both of these are over 1. So basically what ends up happening when you divide by something with a negative power is that negative power actually ends up in the numerator being multiplied, so I actually end up adding those powers together, which would give me s to the 4/2 power, which is just s squared. So one more time, s to the power of 3/2 divided by s to the power of -1/2 turned into s to the power of 3/2 divided by 1/s to the power of 1/2. But I'm dividing, so then you end up multiplying by the reciprocal, so it flips over again, or this negative moves to the top basically and becomes times s to the power of 1/2. But now that I'm multiplying common bases, I add the powers. So 3/2 plus 1/2 became 4/2 or 2. So back over here to my problem, this s to the 3/2, when I divided it by s to the -1/2, becomes s squared. So hopefully you're kind of seeing our other simplified answer sort of take shape here. Then when I divide s to the -1/2 by itself, they just cancel out. And then when I do 4 divided by 1/2, that's the same thing as 4 times 2/1, which is the same thing as 8. So 4 divided by 1/2 becomes 8, and so this is the other way that you could simplify this type of problem. So I call this the factor out the negative exponent way. Factor out the negative exponent, because sometimes that's what the AP test does. Like if they have multiple choice answers, they would simplify their answer this way. So like let's say you're doing the problem and you simplified it this way. You would just need to recognize that these are the same thing essentially. One of them is thinking of it more in terms of a common denominator radical, and the other one is thinking of it more as like a common factor of a negative power that's been pulled out. So it's important for you to know both. Now, let's say it's an open-ended question. Like, let's say I ask you, find this derivative, and I'm just having you fill in your answer. I am okay with either or. I will not require any certain way, because I like them both. I think they both are good for different reasons. I have no preference. I do suggest, though, that you study this one and learn both methods of simplifying for the AP test. Okay, how about you guys try one? This one will be not nearly as bad as part B. This one's reasonable. Go ahead and give this one a try. So in the you try, we had both a product and a subtraction, a difference. So for the product part, we had to use the product rule. But for the subtraction part, we just used the sum and difference rule, which just says, hey, find this derivative separately and that derivative separately, and then just subtract them. Although I kind of thought of it as adding a negative, but either way is fine. So for the first part, I had to use the full on product rule, f prime g plus g prime f. So for f prime, that was just a 2. For the derivative of, for g, it's just cosine, so it's f prime g. For the derivative of g, that's negative sine. And then f of x was 2x. And then the derivative of sine is just cosine. So the derivative of 2 sine x was just 2 cosine x. And that was being subtracted just from the original question. So the 2 cosine x's actually canceled out. And I was just left with negative 2x sine x as my derivative for y. So in example 2, now we're beginning to look at things that are going to require the quotient rule. And you can see here, like this is in terms of f of x. So it might be confusing to do f prime g and g prime f. So maybe for these examples where I have f of x, maybe I'll use the u and v version. So I'm going to say that u is the 5x minus 2 function and v is the x squared plus 1 function. So I'll write that down here. And then I'm going to say that u prime would just be the slope of this line, right? Because the derivative of a function is just its slope. V prime is going to equal 2x based on the power rule, and then plus 0 based on the derivative of a constant rule. Derivatives of constants are always 0. So then f prime of x, if I write out the rule, which I recommend you do when you're learning it for the first time, just to get better at it. So it's the derivative of the top one first times the bottom minus derivative of the bottom times the top all over the bottom squared. So in this case, that would be 5 times x squared plus 1 minus 2x times 5x minus 2 all over x squared plus 1 squared. So then I'll do some distributing and simplifying, and don't forget to distribute the negative as well. So I get 5x squared plus 1 minus 10x squared plus 2x, because I get negative 2 times 5, that's negative 10, and then negative 2 times negative 2, whoops, that should be a 4. So plus 4x. Okay, and then all of that again is over x squared plus 1 squared. So then I can combine my like terms. I've got a 5x squared and a minus 10x squared. If I add them together, I get negative 5x squared. So I get negative 5x squared plus 4x plus 1. I went ahead and put it in descending order. And then all of that is over x squared plus 1 squared. And so that would be our final answer for f prime of x using the quotient rule. Let's try another one where I'm finding f prime of x, but then I'm also going to find the derivative at a point, just to remember that that's a thing we do sometimes too. So again, I'm using f of x as the name of the function, so maybe I'll use like u and v for writing out my quotient rule so I don't get confused. So I'm going to let u be the numerator, x minus 4, v is the denominator of x plus 4. So then u prime would just be 1, just the slope of that line, and then v prime would also be 1 because both of these are linear functions with slopes of 1. So then f prime of x would be, let's say it out, u prime v minus v prime u all over v squared. Derivative of the top times the bottom minus derivative of the bottom times the top all over the bottom squared. Okay, so now let's fill that all in. So then u prime is just 1 times v was x plus 4 minus, don't forget quotient rules, minus derivative of the bottom, which also was 1, times the top, which was x minus 4, all over the bottom squared. And so then I end up with, if I distribute this negative, I end up with x plus 4 minus x plus another 4 all over x plus 4 squared. And so I can see that my x's will actually subtract away, and then these 4's will add up to 8. And so I will end up with a derivative of 8 over x plus 4 squared. So that is my derivative as a function of x. So this would give me the slope of any tangent line. The slope of any tangent line to f of x at any x. Right? That's kind of what f prime of x is. It's any slope of any line at any x. But let's suppose I wanted to find the slope at like one particular point, 3. So then I could do f prime of 3 and just plug 3 into my derivative at x. And I'd have 8 over 3 plus 4 squared, which would be 8 over 7 squared, which would be 8 over 49. So that would be f prime of 3. So what is that? That would be just one particular slope. The slope of the line that was tangent to f of x at x equals 3. So it's one particular tangent line at one particular point versus a function. So just kind of wanted to review that concept as well. So why don't you practice using the quotient rule right here? You try one. Okay, so for this you try, you might notice it did require some simplifying, not as complicated as our example earlier, but did involve going back and forth from radical notation to rational exponent notation and combining these powers. But let me just start from the beginning. So the numerator is like our u function, our f of x. The denominator is our v function, or our g of x. So u prime was pretty simple, it was just 2x. V prime, though, I had to think of v as 2x to the 1/2 plus 1. So then if I use the power rule, I would multiply the 1/2 to the 2, which turns it into 1, and then subtract 1 from the power, which turns it into negative 1/2, and then the derivative of 1 is 0. So you could either think of it that way, x to the negative 1/2, or as 1 over the square root of x, which is how I plugged it in my answer. So then you do u prime v minus v prime u all over v squared. Now when you distribute the 2x to the 2 rad x plus 1, then you get 4x rad x plus 2x. But remember, rad x is the same thing as x to the 1/2 power. So you can and should combine those powers. This is a first power and a 1/2 power. So you can add those powers together to get a 3/2 power. Meanwhile, you could think of this as a negative 1/2 power, or it's dividing by a 1/2 power. So you're subtracting powers. 2 minus 1/2 is also 3/2. Because then we can recognize that these are like terms. 4x to the 3/2 and then negative 1x to the 3/2. And so we can combine them to get 3x to the 3/2. That's the only real simplifying you have to do. So you could either leave it like this, or you could then go back to radical notation, remembering that x to the 3 over 2 is x to the first times x to the 1/2, or x rad x. So either one of these answers would be fine. So in example 3, I just wanted to give a couple examples of when you might get tricked into thinking you have to use the quotient rule when you don't really. You can save some time. So recognizing things like f of x could be rewritten as a constant of 9/5 times 1 power function, right? Because you can think of the numerator as 9 times 1. So 9 over 5x squared is the same thing as 9/5 times 1x squared. And you can even think of that as 9/5 times x to the negative 2. So instead of having to go through the whole quotient rule, you could just use a power rule. So the derivative here would just be, you just multiply 9/5 by negative 2, so negative 18/5. Subtract 1 from the power, that's x to the negative 3rd. It would be good to write it back, with x in the denominator, so that's negative 18 over 5x to the 3rd. And you're done. So I would just recommend keep an eye out for times when you don't have to use the quotient rule and when you can save some time. And B was another example of that. You would need to distribute the negative 3 at first, and you get negative 9x plus 6x squared. But because they have a common denominator, right, a single denominator, you could just divide both of them by that denominator separately. And this part, the x's cancel out completely. So you have negative 9 over 7. And then in the second part, they don't cancel out completely, but the denominator does. So you can just think of that as 6/7 times x. And then this is actually a linear function, right? The derivative of a linear function is just the slope. So the derivative is just 6/7. So it's just things like that. If you can recognize right away that you can simplify the expression to where you don't need to use a quotient rule, I would advise doing that. So in example 4, we are revisiting this idea of a second derivative, which is the derivative of the derivative. So the notation we use is either y double prime, or we can sometimes say d2y over dx squared. Or maybe you might see that as f double prime x. But basically the way you find it is to just take the first derivative and then the derivative of the first derivative. So in part A, I'm just going to do the first derivative of f, which I'm going to use the power rule. So I get 2x, the constant multiple rule, so I get 6, and then the constant rule, so I get 0. So 2x plus 6 plus 0. That's the first derivative. So then the second derivative is just the derivative of the derivative. So now I just take the derivative of 2x plus 6. Since this is now a linear function, that would just be the slope. So there's my second derivative. So sometimes derivatives get easier as you go from one to the next, and sometimes they don't. So something like B, I would have to use the quotient rule twice. So let's just start with it the first time. So I'm going to let u represent x and then v represent x plus 1. So then u prime would be 1, and actually so would v prime because they're both linear functions and they each have a slope of 1. So then g prime of x will be u prime v. So 1 times x plus 1 minus v prime u, 1 times x, all over v squared. So then if I simplify that a little bit, I get x plus 1 minus x all over x plus 1 squared. And then I notice that my x's cancel out. So actually this one did get a little simpler, thank goodness. That doesn't always work with these quotient rule ones. Sometimes they get more complicated. But that's my first derivative, that's g prime. And then what I'm going to have to do is take the derivative of that. So then I have a new u and a new v. So now u is just 1, which is the numerator, and then v is x plus 1 squared. So then u prime would be 0, because the derivative of a constant is 0, and then v prime, oh bummer, I'm going to have to multiply v out. Okay, let's do that real quick. We got to FOIL x plus 1 squared, which will be x squared plus 2x plus 1. We have to do that in order to use the power rule. We haven't learned a chain rule yet. Those of you that know chain rule could use that here instead. But for the rest of us, we have to FOIL this out and use power rule. So v prime would be 2x plus 2. Power rule plus constant multiple rule plus constant rule. And then looks like I'm going to have to steal some space from your you try space. Sorry about that. Thanks for being so generous with me and your space. All right, so we're going to do the second derivative, which is the derivative of the derivative. So now I'm taking the derivative of 1 over x plus 1 squared. Second derivative would be, again, u prime v. So 0 times x plus 1 squared minus v prime, which is 2x plus 2, times u, which was 1, and then all over v squared. So v was x plus 1 squared, and then I'm squaring that. So it's going to end up being, well, this whole first part goes to 0. So that's fantastic, actually. I love that. Love when things go to 0. Okay, so I've got 0 minus 2x minus 2, because you got to distribute that negative. Don't forget, all over what turns out to be x plus 1 to the 4th, because you got to multiply those powers there. So then I have negative 2x minus 2 all over x plus 1 to the 4th, which can be simplified, which means it should be simplified, because I can take out a negative 2 in the numerator, giving me a factor of x plus 1. And then I can cancel one of the factors of x plus 1. So my final answer for the second derivative of g, that means the derivative of g, would be negative 2 divided by x plus 1 to the 3rd. So when you take 1 away, you're left with 3 factors left in the denominator. So there's my final answer on that one. So why don't you guys try doing second derivatives of these functions here? Okay, so in part A, we just basically had to do a power rule twice. So for the first derivative, I bring the 3/4 down and multiply it to the 6 and get 18/4, and then subtract 1 from the power to get negative 1/4. And the 18/4 reduces to 9/2. And then for the second derivative, I do that again, basically another power rule. I just multiply 9/2 by negative 1/4, so I get negative 9/8. Subtract 1 from the power to get negative 5/4. And then you can either leave your answer like that, or you can bring the x to the 5/4 down to the denominator. And there's our second derivative. For b, you can see these functions just alternate back and forth. So the derivative of cosine is negative sine. And then the second derivative of cosine would be the derivative of negative sine, which is negative cosine, because the derivative of sine is cosine, but then this is being multiplied by negative 1. So then it's negative 1 times cosine, which is negative cosine. So for our final example in this video, this is a very classic AP style question where they don't give you any equations. They just say, oh, this function p of x is equal to a product of two functions, f of x and g of x. And then instead of giving you their equations, they either give you like a table of values or maybe a graph like the one we see here. So what you should do is use the general rule. So I'm trying to find p prime of 0. But before I find p prime of 0, I need to understand how we would calculate p prime of x, which is the derivative of a product. So I would need to use the product rule. So we just write out what the product rule is. F prime of x times g of x plus g prime of x times f of x. Write it out first with x plugged in, not 0. Then after you have the rule written out, then go ahead and plug in 0. And I just want to note here that we want to remember it's the derivative of the first function times the second plus derivative of the second times the first. So then what we do is we plug in the 0 values for x. So then we say, okay, p prime of 0 is f prime of 0 times g of 0 plus g prime of 0 times f of 0. So then what is f prime of 0? F prime of 0 would be the slope of f at x equals 0. So I go over here to my f graph and I can see that all the way from -1 to 1. So that includes 0. It has a rise of 2 and a run of 3. Rise of 2, run of, a rise of 2 and a run of 1. So it goes up 2 over 1, up 2 over 1. So it has a slope of 1 for that stretch of the graph, which includes x equals 0. So that would work for f prime of 0. So this value would equal 2. And then g of 0 is the value of g. This is just the y value of g at x equals 0. So then you just find the g function at x equals 0. It's right there. It's at 0, 2. So that's my value for g of 0. G prime of 0 would be the slope of g at 0. So let's get this out of the way. So I can see that for all of this left side of the graph to the left of 2, which includes 0, it's going down 1 over 1, down 1 over 1, down 1 over 1. So the slope is -1. And then what's f of 0? F would be the y value of f at x equals 0. So in this case, that would be 1. 0, 1. So then this value is equal to 1. So then what is p prime of 0? It's just 2 times 2 plus -1 times 1. Once I went ahead and read all those values off the graph, that's 4 minus 1 is 3. And then in this last example, we are going to do a similar process, but now we're looking at a quotient of two functions. And we're trying to find the derivative of that quotient at 4. But before you plug in the 4, you should kind of consider, well, how was the derivative of q prime of x calculated? Because q of x is a quotient. So we should write out the quotient rule, which is derivative of the top times the bottom. So f prime times g minus the derivative of the bottom function times the top, g prime f, all over the bottom function squared. We should write it out generically first and then plug in 4 to every x. So what would that be? That'd be f prime of 4 times g of 4 minus g prime of 4 times f of 4, all divided by g of 4 squared. How do I find these values? Well, I'm going to take it over here to the graph. Maybe I'll zoom in a little bit so we can see it a little clearer. So f prime of 4 would be the slope of f at 4. So I go over to 4. F is horizontal at that part, so the slope along that part is 0. So then f of 4 would be 0. G of 4 would be the actual value of g at 4, like the point on the graph at 4, which is 1. So g of 4 is 1. G prime of 4 would then be the slope of this middle stretch that includes the x value of 4, which looks like it has a rise of 1 and a run of 1, like it's going up 1 over 1, up 1 over 1, that whole stretch. So g prime of 4 would be 1, so that's the slope of g at 4. And then f of 4 would be the y value of f at 4, which is down here. The y value of f at 4 is -1. And then we had calculated g of 4 earlier to be 1. So then if I'm going to finalize my answer for q prime of 4, I have 0 times 1 minus 1 times -1 all over 1 squared. Lots of zeros and ones. So then I get 0 plus 1 over 1, so I just get 1. So the derivative of q, which was the quotient of f and g, at 4 is 1. That concludes our video. Thanks for hanging out all the way to the end. Props to you, and I'll see you in class.